Hello, everyone. Thanks for showing up to Infinite Scale Illusion, or navigating the pitfalls and limitations of large-scale computing on Azure. My name is Michael Wittemer. I'm a principal software architect at Silke. I'm doing mostly Azure cloud-related stuff in IoT and data platform development. In general, have a passion for distributed systems with any data-intense domain. And in that particular large-scale batch processing. So about today, I thought that I want to do this in a kind of interactive session. So in case there are questions popping up, feel free to ask. As for the agenda, first I would like to give you an overview on what is the project that I'm going to talk about. So as you might have read the abstract, I want to guide you through a project of mine that I've been doing over the course of the last 6 years. First more intense, nowadays more on a sporadic engagement there. And along this project, where we started with an on-prem stuff, we got into the cloud and had several interesting observations, several pitfalls that we experienced that we wanted to overcome in order to get a robust system. And finally, also, if time permits, a bunch of lines of code, as this is still a developer conference, and I think code is mandatory. So about our journey to the cloud, or in other terms, what is actually the project that I'm talking about? It's called Actuarial Factory, and it's in the insurance and finance domain. First, sounds kind of boring, but from a techie perspective, super exciting, because you got a lot of computations you need to do there. You have a problem that you want to, your company has a private pension fund, for instance, and they need to compute several numbers for some report, whether the amount of money they need to hold back or keep in a reserve. And if we break it down for us, what does that mean? So as I said, we have a large number of individual independent computations. So you do something in a web UI first, and later on compute those numbers. And it's very CPU intense. So we don't need much memory, RAM. A bunch of gigabytes is sufficient, but plenty of CPU. So to give you an understanding, we are scaling there at some points in time during seasonal business up to 150 machines computing that stuff with 2 cores each. So that was, as so far, the maximum that we had been using. We could go beyond that, but would have to scale certain other parts of the system. So for instance, the database we're using. And as you might expect, this is a highly fluctuating usage pattern that we have. So the people using that software are approximately 30 people working with it. When they have office hours, we have a high usage. When they're outside office hours, we have little to none usage. Sometimes during seasonal business, work hours might be a little longer. Sometimes they might do computations overnight, but still there is a huge potential to save money during the times when this isn't used. As we all should keep in mind, the resources we aren't allocating are the cheapest ones. So to give you an understanding on how we can actually scale there. So this is like the perfect example on using parallelism for scaling. So we are computing a large company with, for instance, 10,000 people being employed there, and we need to do precisely the same computations for every individual. So we are simply chunking up those 10,000 people into slices or into chunks with, for instance, 20 people. And we can do these 20 people in parallel and only have to do some little bit of work afterwards once we are finished with each of these slices. To do the post-processing part. To give you some more understanding on the number of computations, so we're doing 10,000 people, we're doing 25 results, we are doing projections on a monthly basis for 120 years, which is approximately 1,450 months or something like that. And we are doing that on a sub-second to second basis for an individual person. So quite some CPU time that goes into this computation. So some of you familiar with Azure might ask a reasonable question now: why aren't we just using Azure Batch? It's precisely what I've been describing. So they bring your application, you can put it there, they provide the compute, they take care of provisioning the compute up to, as they claim, 100,000 cores. So should be sufficient for our use case. And they manage the scheduling, they manage the monitoring. Well, as I said, we also have an on-prem part there. So Azure Batch is kind of cloud only. And another part that I haven't been telling there is we sometimes have, we need to distinguish in our computations between two classes. So we have the ones that we are doing the large computations, and at some point we need a report, but sometimes as someone working with that application, you need feedback on the numbers within shorter periods of time. So you need certain iterations and parameterization, and then we need more responsive feedback. So to give you an understanding on what does the system look that I had been building there. First of all, it's a .NET application, uses a .NET backend. We haven't started with .NET 8 6 years ago, but we kept on modernizing our stack, and we are using Hangfire. In case you ever need to do some job scheduling, batch processing, take a look at Hangfire in the .NET ecosystem. It's a nice library for taking care of that stuff. We also have Signalar in there, as we wanted to have WebSocket connection. So whenever we do some computation, we're pushing back status updates to our users. So they're working in an Angular front end, doing their stuff, have a progress bar, for instance, there, get some feedback on what happens on the machines in the backend. And besides that, we have some data storage, which is rather straightforward. It's a SQL server. You can run it in the cloud. You can run it on-prem. And all of the banking and insurance companies are nowadays very equipped in know-how on how to operate SQL Server. And in addition, we have some Redis cache, which is for the entire application optional, but it supports caching, scaling, does some of the message broker features that we are using there.
But is it running on premise as well? Or is it
it's running on premise as well. The same application can be executed on prem. So it's just a monolithic .NET application. You can run it on prem, but with some config tweaking and certain strategies that are available, which I'm going to come later, you can use some of the cloud unique capabilities. And originally, we actually started on-prem. The entire thing was built for on-prem. We only later migrated, which is going to be part of this talk as well. And yeah, in the back end, in the very back of the application, we are using virtual machine scale sets for executing the actual computations, while in the front-end part, we are using an app service for doing the web application stuff. Again, the same application being executed on both parts of the system. The reason for that distinction is the virtual machines being more capable on the CPU side, being cheaper, being easier to scale. We can go into that in detail, while the app service on the other side takes a lot of effort in managing certificates, doing the load balancing. It's just convenience for running it as a public-facing API in there. So there is a bunch of theory for that in this talk today, and there is those three key concepts that I really would like you to understand, as they are crucial for understanding the subsequent part. So you might have heard it in school in mathematics, idempotency. Applying a function to the result of the function being applied, it results in the same result. Or in other terms, if we do a computation and we run it a second time, it's still the result is the same. The same is, or something, another important part is having re-entry, being aware of re-entrant. So your job might, as it gets distributed amongst the system, it might have to, the machine might die, or you might lose connection and you simply don't know anymore, is the job still running? You might start it at another machine to do it there. It might have done parts of the computation and would like to continue where it left off in order to reduce the effort that is done for nothing, more or less. And last but not least, preemptive. So you might know it from your operating system, tasks, your process is running there. So if you do large computations, they might take up your entire cluster. And in some cases, someone wants to do a very tiny computation, a single person, and somebody with 10,000, 20,000 people takes up everything. So you might want to have to interrupt that person with their 10,000 people, take care of that one person, give that one person feedback, and then continue on with the other computation. As for our journey, so as I said, we started with an on-prem solution initially, and later on, we migrated to the first versioning and in Azure with the first cloud version. And while it was running, as you could say, to some extent, Azure is just someone else's computer. Don't hurt me for that one. It's not ideal. So you soon see potential where you could optimize in order to get more out of the ecosystem that you have there available. And so we did several optimizations. We did some front-end optimizations because the issues you will see with the WebSockets, with hundreds of machines in the backends are different ones than when you start off with a single, very large machine with 50 cores in a data center, in a local network. Again, is different. And eventually, we are currently working on that. We would like to use spot machines, which is something in Azure. If resources aren't utilized heavily in Azure and they have machines, spare machines, they are discounting the prices a lot. So you could get cheaper machines at times where there is not much need for compute. So going into some theories, potential pitfalls and gotchas throughout the project, or in other terms, there are some fake news on what cloud providers tell you that they are capable of doing it, or I would claim saying so. So choosing the appropriate VM tier in our case. As I said, we have the requirement of a very CPU intense machine. So we had to do had been taken up we have been using a lot of CPU time for our computations. So you might say we have those app service. It's, as I said, it's the most convenient way of hosting your application on Azure. We could simply scale that one. Well, you could do, but on the one hand, those are rather generic CPUs that you get with your app services. They are not very capable in raw CPU power, and they are a lot more expensive than what you get if you really choose the appropriate CPU that matches best your case. And nowadays, something that is very convenient, they have some questionnaire that you can take in Azure, which just guides you to the class of CPUs or virtual machine types that deems appropriate for your use case. To give you an idea, we are using there the F-series CPUs, which are for compute-intense workloads. They have 2 cores, as we decided we want to have a very small machine that we can scale out when we have a demand, do horizontal scaling rather than vertical scaling, and have little memory usage, as said, so the 8 GB is more than sufficient for us. And again, there also the virtual machines, while it has changed over time, the virtual machines were initially the ones that provided discounts on committing for a certain period of time with usage, or they are the only ones that actually provide spot machines. As I said before, you can get an up to 82% discount if they aren't using their resources intensively during that time. Which brings me to one of the very first or second theory slide, I would say, rapid elasticity. You might have heard that term before. It basically means I would say it's a cloud key ingredient. So this is like one of the things that really distinguishes your or differentiates your cloud environment from your on-prem data center. The fact that you can easily adopt your compute resources to the needs of your application in any point in time, which is crucial in order to save money. So you're basically giving back the machines when you don't need it. And thinking about our 9 to 5 office hours, you aren't using them after 5 in the evening. You aren't using them before 8 in the morning. You aren't using them at weekends, so give them back. So doing a short reality check on that rapid elasticity. It works quite nice with virtual machines. So your virtual machine scale set, you can host up to 1,000 machines in one scale set, and you get them like really most of the time, or almost always. It takes a bunch of minutes, like 5 minutes for a machine to pop up once the scaling decision was done. And there are some features, sometimes it fails, and there are some features to cope with that potential failure during scaling, so the over-provisioning, which is, again, something that you need to be aware for your application. It can be the case that a machine just pops up for a bunch of seconds, does some mess to your system, creates some load on the database, and is gone afterwards because it's not needed, because nobody else failed during scaling. So this is like just the functionality by Azure that allows you to say, I want to have 40 machines. We are provisioning 45 or 41 machines, for instance. And in case one of the machines fails, you still have your 40 machines that you requested. In case none of them fails, we're just throwing that one excessive machine away once we know that they are all healthy and up. Well, when we go into the app service, the scaling is again a lot different. So an app service claims you can scale from 1 to 30, 1 to 40, depends machines within that app service tier. In theory, I would say, because you're there at your app service, you have now one machine running. There is still some underlying infrastructure, and you being able to scale to 30 machines from 1 minute to the other depends on that underlying infrastructure. You can't really see it from your perspective. From the portal perspective, it looks like there is a slide. I can simply drag it to the very end of that. But if you do so and click the save button, more or less, you might end up with an error. The system might tell you that at this point in time, you can only get like 14 machines because there is no capacity underneath it.
Okay.
So from the perspective underneath, they're using, again, virtual machine scale sets. So they are packing your applications on their clusters of virtual machines. Yeah. And if you're unlucky or not unlucky, so they try to optimize it. So if you're currently using one machine, it's very unlikely that you will a minute later use 30 machines. So it's simply not built for that kind of workload.
Because the slogan is actually that you get as much computation power as you want, right?
The slogan is that, yes. If you would want your application to have 30 machines, you would have to delete your app service and redeploy it, the app service plan, because initially you would have the capacity, and they are re-evaluating every 6 hours in order to allow you to scale up or down. So if you scale to 14, 6 hours later, you would be most likely able to scale to 30. But it's just the case that you might not be able to scale to 30 initially because you are at the cluster that is currently not that huge. And another part, as I said, we have a SQL server in our database, and there is very little flexibility in scaling SQL server, especially the provisioned one, because there is this serverless version of SQL Server that scales very nicely. It does it for you under a hood. You just define certain boundaries of minimum vCore hours, maximum vCore hours, and it takes care of it. But that's expensive. It's quite expensive because a single vCore hour with a serverless tier is about 3 times the price of the provisioned one. So you need to do the math if this is really a use case for you to operate your application using a serverless tier of your SQL database. On the other hand, the provision tier, it gets cheaper, but once you scale, in the one hand, it takes quite some time to scale, but on the other hand, it drops your database connections, it drops your transactions, which is annoying to your applications, to your users. And last but not least, Redis, as I said, is also part of our infrastructure. That one has little to no support in scaling down. So once you have grown your memory cache, there is no way back from the standard tier to the basic one or things like that. So there are limitations. So my recommendation would be, once you decide on using a certain service, or once you think about using a certain service, go into the documentations, look up the quotas, look up the limitations that service comes with, be aware about the pricing, and do some math. Excel is your friend on how much that thing is going to cost you. And if the serverless thing that claims to stop for an hour, for instance, when it's not used, is really worth the effort, does it really bring you any savings? Because you need to be aware, once it's stopped, it takes half a minute, it takes a minute to come up again. So your request might time out. Your application needs to be aware of that initiating a SQL connection when your database is turned off takes 30 seconds. So your average .NET Entity Framework SQL connection would time out. There is a retrying strategy taking care of that. It still fails sometimes, but that has its own drawbacks.
Over provisioning, do you have a recommendation on a percentage how much you should over provision, or is this, so where does it depend?
There is no setting as in the amount of over provisioning. The system takes care of it on its own. So you can either say, I want to use the over provisioning in order to have be more successful in my scaling operations, or I would like to disable them at all and avoid any over provisioning. So one step further, resilience by design. So if you build a system that is stable in a stable environment, it will be stable only in that stable environment because it will only work there. So if you build your system that it can work with machines dying, with not behaving as expected, being having more latency, like the SQL server turning on, then it's definitely going to work in the stable environment. But it will also survive in the chaotic, not so stable environment. So while our initial system was having its database in the local network, it was on a single machine. We of course had certain things in place to cope with the process dying or something like that. But it was a really friendly environment. And the moment you start using 150 machines there is always something that is not working precisely as expected throughout the day. And if you're doing a very large computation that takes several hours to complete, if one of them machine failing is sufficient for your entire computation to fail, it really sucks. So you need to be able to cope with that one machine dying and still complete your application. So that's where we are again at that re-entrant, idempotent, preemptive part that we had in the beginning. And as I said, things are different reasons why it might fail. It might be a networking issue, a transient one. It might just be your database connection dropping. or your scaling operation failing in a virtual machine, or simply your application running out of memory because you did something, you did an error in your programming and you had some function that allocated a lot more memory than you expected. And last but not least, your users, they might not behave as expected. That sometimes happens. And as you can expect, when you scale from one machine to 50 machines, you're having different loads in your system. And when you're triggering large computations, it automatically triggers a load spike in your system. So what is actually meant by this load spike? It's actually a change in the amount of resources needed in an unpredictable way, or due to your business behavior, due to your application behavior. In our case, for instance, at 9 in the morning, when everyone logs in, we usually have, of course, a spike. When everyone clicks 10 minutes later, start my computation, we again have a spike. When compute bins are completed and others start, they are of similar size, so they start at a similar time, they end up at a similar time, so you keep on having the same spikes over and over again. So you start having heuristics in order to make your bins of different sizes. So for instance, as I said in the initial graphics, I said 10,000 people, 20 people each slice. That's a bad idea, actually. Use 15 people in one, 25 in the other, do some random in between on how large you create your slices, and a lot of these load spikes will even out over time. The other thing is you need some calibration on how much or how huge you should create your slices. If they are too big, it takes a lot of time for them to complete. So you need to interrupt them, having been able to interrupt your computation. You need certain checkpoints where you can stop them, hand over to another machine. Because if you scale down, for instance, so you had 150 machines and you're scaling down, the system doesn't really let you choose which machines are going to be removed. So they're just going to remove the oldest, the newest, some random machines in order to create highest availability, depending on your configuration in Azure. And on that machine, it might be the case that some application is still running and doing something. So you need to be able to migrate that job to some other machine. Some other machine should take over. And typically, one wouldn't expect that load increases when you scale down, but it does, because those machines are going to be taken away and they need to fetch their data. When your compute starts, it needs certain starting information on what do I need to compute, what is the input that I'm going to use. So it contacts its SQL server, fetches that data, while the queries are point reads, efficient. If you do it from 100 machines in parallel, fetching a certain amount of data, your SQL server will experience a certain amount of load. We have to admit we are using the smallest size in SQL Server there for that system, but still we see kind of spikes in precisely these moments when we're scaling. Well, and another thing that you should keep in mind, if your SQL Server has then experiences these times of high pressure or high load, it will again influence your user experience as well, because you're using the same database. It's not just that you can say, okay, it will do its job. It's under pressure for a minute and then it's okay again. During that time, your front-end requests will suffer as well. So you should avoid these times of high pressure, either CPU, either log, either data IO, depending on what you are using in the SQL Server. So since I've said a lot already about strategic scaling and the problems that arise with just reacting from your system perspective to the scaling that happens in the system, another thing that we did was we incorporated knowledge about our application, about the data that we are using in order to make better scaling decisions. As I already said, the chunk sizes, having a heuristic that estimates how long is my package gonna take to complete, because our application is highly customizable in the type of computations you're doing, with the single computation ranging from sub-seconds to multiple seconds. So that makes, again, already a factor of 100 or something like that in the duration a package may take. And you would still want your package to acquire a certain amount of CPU time when you provision machines. And I'm going to go through that example, so don't try to read it and understand it right now, but I'm going to go through that with you together. When we scale, it takes 5 minutes for the machines to pop up. So we don't want to scale, use them for 2 minutes, and throw them away afterwards immediately again. So we always have trade-offs. Scaling raises 5 minutes of costs we aren't utilizing. We are just paying for that machine to be provisioned, but we aren't using it for any good. So we want, for instance, in my very trivial example, we would like to use our machines for at least 15 minutes after scaling. And we also know about our machines that they have 2 cores each machine, so they can take 2 computations in parallel. And they take approximately 5 minutes to start. And we, again, also know that our SQL database works best if we keep the amount of machines under 50 or under 60, something like that. So we have 100 threads hitting our database at the worst, something the SQL Server can cope with very well. Again, an important criterion, because the amount of SQL connections you can open to a database are limited based on your tier. So don't go beyond certain thresholds, because your database, your applications won't be able to open SQL connections. And as for my example, I said we are computing there 1,000 people with 3 times 20 results, so 60 results each person, and a result takes a second. So these are not actual numbers, they are just for demonstration, chosen a bit easier on us to follow. So we have in total 1,000 minutes that we are spending there on the computations. So if we think about it, how many machines, we are currently operating 5 virtual machines, and we still would like to finish that in an efficient yet timely manner, the computation. So how many machines should we add? So if we do the computation there, it tells us we should use 22.5 machines, simply by subtracting, dividing the CPU times. And we know we should add 17 machines. Again, all of that is built on heuristics in order to have these estimations. They can be really wrong for a single computation, but on average, they're working quite nicely, and the formulas aren't overly complicated in order to do these kinder estimations. So coming back to our journey, we all started. Sorry.
How did we come to the values in the last equation?
How I got there?
Yeah.
So if you have 1,000.
No, the last line on
the last line.
Yeah.
The equation is actually written up there. So if you have 1,000 machines times the 10 jobs that you can do in the 5 minutes that it takes to scale. So you're removing 50 people are already done at the point when those machines get available. So you still have, from that point in time, you still have 950 people to compute. Since we assumed that each of our compute slices has 10 people, we can't use any more than 90, I actually 95, so my number is wrong. Anyways, you might add one more machine. So you have a limit on the amount of parallelism that you can use. So adding more machines than adding more CPU cores than machine chunks you have to compute doesn't make sense. So a chunk is the smallest unit that can be given to a machine in order to compute.
How do you get to the 22.5 one?
Because I said I'm gonna compute at least 4 jobs on every machine. So with the 50 minutes of VM acquiring the machine, so we're using 5 minutes for scaling, 10 minutes for compute. We're at least doing 4 slices on one machine over its lifetime. So I was simply dividing the 90 by 4 to get the 22.
Thank you.
To be fully open there, the used formula in production is different from that one. I made up that example to demonstrate what these kind of heuristics could actually be.
Did you get to the 1 second per result? Did you emulate this locally, if that's possible, or did you just guess basically, hey, we kind of try this VM
measurement. It's a measurement. So we have, for certain types of computations, for certain use cases, we know have kind of a number on how long it will take.
This was like given already.
This is input to, so all of that is kind of input to my heuristic on deciding on how many machines.
How did you evaluate how long the job takes, the CPU intensive part?
Simply by running it, collecting information
on the VM,
on the machine. Yes.
So like how do you even decide then which machine to take? Because like really, is it like a guess, and then like let's take the next one because the current one is too slow, or vice versa? Since the machine that you
the machines are all equal, so these are all.
But you selected a tier.
Yes.
How do you get which?
Now I got you.
Yeah.
So first we did a bunch of tryouts with we created a sample computation, something that lasts for a bunch of minutes, and we tried that one with different types of tiers on different virtual machine types, and you then have simply the numbers on how long it will take for that machine to compute that computation, or to finish that computation. And you also have the amount of money you're paying for that machine. And when you then correlate those two numbers, you will find some kind of sweet spot on what deems the most efficient way of doing that computations. Well, again, revisiting the journey that we have taken and the steps and the reasons behind them. So as I said, we started on-prem with a single machine with 48 cores doing all of that. We already had the chunking up our computation in slices in order to allow new computations to start with higher priority and all of that. That was there already on-prem. Worked okay-ish on-prem. It's simply the fact that 48 cores isn't that much for such an application. But that was what was again a money versus computational power decision that we ended up with that machine. Then we got into the cloud and we said, we are going to go horizontally with our machines. So we chose the smallest unit that kind of makes sense to use. So there is the possibility to use a single CPU core also, but you need to keep in mind your operating system requires a certain amount of CPU time, requires a certain amount of memory. So the 2 cores were simply provided most space for us to utilize. And we started there with a system that wasn't able to interrupt, was non-preemptive during the computations. And you can still create the system in a way that it's stable and that it does works in an environment when connections drop. But invests, you need to pay for that. It invests in doing computations several times. And in case you're doing scaling, back in those days, we did the scaling in a reactive way. Basically, we measured the amount of CPU time that we had been using at the scale set, and we simply reacted with some formula. If it drops below 30% CPU utilization, just remove 10% of the machines or something like that. And if your system isn't able to preempt your computations, they will start somewhere else again and do the exact, if the machine simply dies after some timeout, because this hangfire on its own is already able to reschedule your computations if they aren't given back or return. There's a heartbeat mechanism if they aren't telling the system that it's still alive. And so we had to recompute a lot of numbers, which simply burns money for no gain, because you scale once, a few minutes later you scale again, and you might kill the exact same package several times, which is expensive and sucks from a user experience, because you started your computation and you have done 90 out of your 91 packages already completed, and the very last one keeps dying and dying and dying and retrying. So we had to do some optimization there. And we decided, well, we know within the package, we simply have some means of code to detect where we left off during computation and simply continue from there, just counting the amount of person that we have computed and do the remainder. That already gave us a lot of possibility to save money and improve the user experience. Another point was, I said we are using SignalR for scaling out our application and for pushing back information about what has happened on the different machines in the backend. And SignalR is a very nice library. It uses WebSockets and has fallback mechanisms. So it allows you to have this real-time communication channel to your browser. But if you use it like we had it initially, it requires sticky sessions with your web application. So basically, if you scale your front end, you need to enable sticky sessions in order to have every request arrive at the same physical machine or virtual machine in that case, application instance to handle your request, that all of that works. Which basically means if you have 30 users and you notice that there is a need to scale out, you're only scaling for the new ones. And there aren't so many new ones. So adding machines doesn't bring value because you're just having them at spare for somebody who isn't using your application. So we needed to get rid of the sticky sessions. And this is where SignalR service comes in very handy, because you hand off all of that connection stateful requirement with the sticky sessions. You give it to a service that is actually built for holding your WebSocket connections, taking care of that, and your backend system can now be fully stateless, doesn't require any application request routing anymore. So you can just hit the load balancer that points you to some machine to take care of your request. Another thing that might be obvious anyways, we also had a lot of potential to improve on as simple as Entity Framework. Be aware of your projections. The moment you split your database from your compute clusters, you split it from the system level, it increases timeouts. The amount of data that is actually transferred between one system and the other is enormous, or can be enormous without you noticing on your on-prem system. We didn't notice, we didn't see it. With our test data, that was simply too low, too small. On my local machine, I never noticed it. You only see it in production, and you don't have hundreds gigabytes of databases on your development laptop to notice. And the fact how we noticed was actually quite easy. We simply used the monitoring tooling in order to notice that the database traffic between our compute nodes and the SQL had resulted in 11 terabytes of data being transferred within 6 hours. Didn't even know that you can transfer that much between a SQL server and the virtual machines. So it immediately raised the question, something is wrong there. That can't be true. And as we've found out, we had a join there, which was, or several joins. Sounds good on first sight. Doing a lot of joins in your database is not resulting in single queries for everything that you include with your entity framework. But having joins results in something that is called Cartesian explosion at some times. So if you join some table with n entities with some other table with m entities, it results in n times m entities. If you do this with a lot of tables, it results in a very huge data set that is actually transferred then between your database and your system in the backend. So long story short, use proper monitoring. It will guide you through some of the pain points in such a system. And having query splitting in place where it's needed, using projections, getting rid of the fields that you don't care, don't always do select star of something, really has a huge potential. And as I ran over time, I'm sorry for not going into more technical details. I omitted the actual coding part for today, in case someone is still curious on how all of this was built. Just approach me throughout the conference. I'm still there and happy to chat about that or something entirely different. In case you want to connect, feel free. I'm happy to connect. Many thanks.
I'm not sure whether I have it still right in my mind, but are you using all the spot machines for production environments?
Not yet. We are still planning on doing so. So right now we would be able to use them from a technical perspective. We first had to create the being idempotent in the computation, being able to be reentrant, to preempt things. And the next step in our case, actually, we also integrated something that emitted. There is this instance metadata service in Azure that provides you with notifications upfront when a virtual machine gets turned off or when something happens to your environment. And we are currently monitoring that one in order to detect that our machine will be gone. This is crucial because for the spot machines, you will get only 30 seconds of notification in advance. And you need to do a proper handover of your remaining work back to the system in order for not requiring fallback mechanisms to detect that your machine has died.
That would have been my next question, because as you already mentioned, you can't rely on the spot machines. So you check whether you have to release the spot machine, exactly. Then you put the things back. So you just take it to get over some peaks.
No, I would actually use them. So on the one hand, spot machines, it's like you define a maximum price that you are willing to pay for your spot machine, and the price increases. And if you go beyond this, if the price goes beyond what you are willing to pay, you will get ejected. Or if there is high demand in Azure for machines, you will get ejected as you are considered a low key, a low priority workload. And before that ejection, you're notified for 30 seconds in advance. This is like guaranteed to you that you will get that notification.
And there is already some out-of-the-box automatism to get all the data to a different virtual machine.
This is where Hangfire takes care of. So Hangfire is our job scheduling library. We submit the jobs there. They are stored there, in our case in Redis, and your machines simply fetch a job from there and do the computation. And if we hand back the release, their lock on that job, someone else can take it over.
Can also use a spot machine for a node, for a Kubernetes cluster.
I think there is some support for that, but I'm not sure. So I think with the node pools in Kubernetes, you can actually use also spot machines, but I'm not sure.
Thanks. Sorry for the questions.
Since it's a CPU-intensive workload, have you also invested time and effort into optimizing that via, for example, hardware intrinsic vectorization and all that?
We did the very basic. Yes. So we already told that we should end. So those of you who want to continue asking questions, discussing, feel free to do so. Otherwise, don't feel required to stay. We used memory layouting in a way that we optimize for cache lines and things like that by simply providing structs over classes, by doing things like ref pointers, etc., for accessing the data and modifying the data. We do this kind of homework. We don't have that much potential as for the type of computations we are doing to use any vector operations. We looked into that, but haven't seen much for these advanced vector extensions, etc., in order to get more efficient on that side of things.
So then they may
nowadays
support it on the VM as well, wouldn't they?
Yeah.
Okay.
They will. The extensions, I guess, are supported,
Yeah.
but the fact that we are doing computations mainly to primitives, for single primitives, we aren't doing them to a larger number to simply to a vector. So it doesn't help that there are vector support if there is no vector.
Did you see performance improvements or reducing over when upgrading from one .NET version to the next? Because there was like always this
huge improvements.
This little blog post, but it's
improvement.
actually a book of the performance improvements. So yeah.
We enabled tiered PGO in the .NET 6 release, and there was again a huge gain in comparison .NET 6 to .NET 8. So Microsoft or the team for .NET did us a huge favor in investing in performance. So we actually, some of the issues that I've been describing in load spikes and things actually only showed up due to performance improvements. The load on the database got a lot heavier because we're spending less time on the machines computing and more time on fetching data, putting data back. So challenges come from performance. Well, I think we should go for lunch.